working before. I don't know what happens now. Why it ignores me?
Okay.
I will switch off and switch on again. Okay, that's good. So I'm a physicist. So I will have some initial slides with some introduction. So in physics, central problem is to understand the properties of many body systems, quantum many body system, quantum physics. Okay, so this is because of many things. So if you want to understand properties of material, sometimes quantum materials, you need to understand how quantum particles interact. Also now there is a very exciting moment in which in the labs, people are preparing systems of say 100,000 of particles under full control. So you have, to have quantum phenomena, to see quantum phenomena for many particles, you have to have these particles under control. And this is what people are achieving now. And this is, and then you want to understand the properties of these systems, and this is challenging. Okay, so I will tell you some paradigmatic problems in these many body scenarios. So the first people care about, okay, you arrange the particles and they interact, and there is a stable configuration, which is the stable of minimal energy. So this is what is called the ground state. So you want to understand the properties of this ground state. Or sometimes you have some parameters, and the properties of this ground state change when you change the parameters. This is what is the phase diagram of the main world system. Sometimes you have a system that evolves and it tends to a steady state. You want to understand the properties of this steady state. And sometimes you want to understand how these properties change with time under some evolution. It's perhaps the hardest problem that I'm listing here. So these are paradigmatic problems that appear in many body physics. So these problems are easy if you have a few particle system. They are hard when you have many particles. Okay? And the only reason why they are hard, it works, but then it stops working. I'm eventually get close to that. And then the reason why this problem is hard in many body regime is because there is an interesting thing happening. This was mentioned by in previous talks. For instance, Frank Westheiter was mentioning this yesterday. So in principle, if you take a textbook in quantum physics, it tells you that if you have a state of an n-particle system, a quantum state, this lives in a Hilbert space of dimension exponential with the number of particles. So this means that to have a full reconstruction of your state, you need an exponentially growing number of parameters, growing exponentially with system size. Okay, this is what theory tells you. This is what you need to say that you perfectly know the state of the system. Well, as you may understand, I mean, it's impossible for you to have access to an exponentially growing number of parameters. Okay, you will have the prepared state. You have no time, and even if you involve your children and your grandchildren, there won't be time for them to compute all these parameters. So this is impossible. Even if you have these parameters, you cannot put them on a computer to make calculations with these parameters. Okay, so this is just not available. But in principle, this is what you need, but you only have, at most, with a high degree polynomially growing number of parameters. Okay, so there's a tension here in what you, in theory, you need and what in practice you have access to. For me, this is an exciting moment in which you have, we have to understand how to deal with partial information to make predictions, or what we are supposed to be partial information. Okay, so we won't have access to all the parameters, and we have to deal with this partial information to make predictions, relevant predictions about the system. Okay, now I'm going to be speculative. This is why I don't write it in the slides. You may even question about the validity of quantum states in this regime. It's something, what is the point of thinking about a ground state? It's just a huge list of numbers that you are never going to have access to. Okay, the vector is vector. Okay, I think this is an interesting moment. It opens challenges for theories and experimentalists in this region. Yes. Okay, so I'm going to spend my talk. I'm going to focus on a paradigmatic problem, although many of the things I'm going to say apply to other regimes, but just for you to understand, I'm going to consider a standard problem, which is, again, you have particles interacting. You want to understand the state of minimal energy, the ground state. You want to understand this state. So sometimes people say you want to compute the ground state. Okay? Well, actually, if you follow what I just said, I mean, thinking that you want to obtain the ground state doesn't make sense. Okay, you don't want the ground state is a vector in a Hilbert space of exponentially growing dimension. Well, it's meaningless to say that you want all the 2 to the n coefficients of your ground state. It doesn't make sense. Okay, so basically, what you want to understand the properties. The properties usually are reflected by this is what I'm saying. Why do you want the ground state? I mean, you just want properties of how these particles arrange. Okay, you may want to know whether the particles, I don't know, they show magnetization, they are aligned in a given direction, or the spins are aligned or anti-aligned. So you want to understand some properties about the ground state. You don't want all the coefficients of your vector. Again, you cannot put them into any memory. You cannot even think about that. So I'm going to take, so usually what you want is because also you can only do that, you want a polynomially growing number of parameters about your ground state property of interest. So I'm going to take one instance of this problem. So you want to compute the magnetization, so whether the spins are aligned in the direction of the ground state. Okay, so this means formally you have the number of particles in your system, you have an operator that is called the Hamiltonian that tells you the energy that grows exponentially very slow with the number of parameters. Then you want to find the state of minimal energy, and of the state of minimal energy, which is the ground state, you want to compute the magnetization. So basically, I mean, naively, what you have to do, you have to find the state of minimal energy. Okay, I'm using this bracket. I'm assuming that that will be okay for this audience. Okay. Okay, so you want to compute the state of minimal energy. This will give you the ground state energy. Then you have the state, and then you compute the magnetization. Okay, so what are the options we have? Well, the first option is
and the thing that at the end is can you go to the previous slide?
Sure.
This thing at the end is a number.
This
thing at the end, the magnetization is a number.
A number, yes.
Yes.
So yeah, exactly. So this is I'm using the bracket, but this is the
this is the inner product.
Okay, the inner product. So this is a number.
Okay.
So this is why you see it's a bit. I will come back to this. I start with this operator. This usually is a Hamiltonian, it's an operator that is defined by a polynomial growing number of parameters. But you will have an exponential matrix. And you have to diagonalize this exponential matrix, you will get an exponential vector. Exponentially growing with n. Okay.
So it's really a number for every fixed big n.
You have a number for any n.
It changes with big n.
It may change, yes. Okay. But I'm also renormalizing. Okay. But this is just an instance, okay? So what I want to say with you is that you are given these interactions, you want to compute the state of minimal energy, but actually you want some properties of this state. Again, this is an exponentially growing number. Okay, so what are the options you have? Well, the first option is to do what I just said, okay? So you are brute force. Okay, this should be so you construct this big matrix, you compute the eigenvalues, the eigenvectors, you take the minimal one, and you compute the what I just said. What is the nice thing? Well, this is exact. So what is the problem? You cannot go very far in system size with this, okay? It's exponential, so maybe you can do it for 30 qubits. I don't know, I'm not an expert on exact analyzation. If you are symmetries, maybe you can go larger, but you don't go very far in system size with this. So this is why people don't follow this. What they do is, Frank's talk yesterday was an instance. So they say, I cannot solve this over all possible vectors. I have some idea about vectors that might be interesting. So I make a guess about these vectors. Sometimes people don't even have reasons, but I restrict my for the choice of a state that is called a set of ansatz states. So what I do, I cannot solve the problem in full generality. I take a subset of these states because I have physical intuition for that. Sometimes because I can't do it for these states, and otherwise I cannot do it. So they restrict the minimization. You see here it's over all possible vectors. This is just over a subset of vectors. But this subset of vectors is chosen in such a way that this can belong for much larger system sizes. And then you compute then you take what people call sometimes in this the ground state. Okay, this is just a minimization of a smaller set. Okay, and then we take the ground state minimization. I hope you understand why I put it in. Okay, what is nice about this? They can reach large system sizes. So sometimes people suspect that this, although you lose information, this is a very good approximation about the physical properties. This is what they hope. Okay. So this is why you can reach much larger system sizes, but again, you have no guarantee about how close this number is to that number. So what is the only guarantee you have in variational methods? All what you can certify is that this number is smaller than that number. Okay? If you have to solve a minimization and you solve a minimization over a smaller set of possibilities, then the actual minimum will be never larger than this number. Right? It's the reality. About how close this number is to that number, we don't know. Sometimes it ignores me. Okay. Okay, so just I will repeat this introduction. Okay. So what I want to say is that you have a starting point, so you have these interactions, and this always exponential matrix. This exponential matrix depends on a polynomial growing number of parameters. This is why I can define the problem. Okay, sometimes, for instance, you have a chain, if you remember Frank's talk yesterday, and what you have to define are the coupling between neighboring particles. The number of couplings you need to define is linear to system size. Then this is an exponential matrix, but the definition of the problem is through a polynomial number of parameters. And out of this, I want to find a subset of parameters, in my previous example, multiplication. Okay, so this is my starting point, and I want to arrive there. How do you do it with, How do you do it with exact diagonalization? Okay. So you arrive there through an exponential effort. Okay, so you may wonder whether this is the right thing. Okay, so you want to write a number from a certain set of numbers, and you do it through an exponential effort. What do they do in variational? You never go through an exponential effort, it's always polynomial, and you arrive to a point that hopefully is close to the one point you're interested in.
New play through that.
Huh? Okay. Maybe it's my fault. I don't know what I'm doing. Okay, so the question we are interested in is this picture complete in the sense that can we get rigorous results about the number the quantity I'm interested in with polynomial effort? Okay, of course I can have an estimation with a polynomial effort, but I have no guarantees about how close this is to one. Or I can find the number I'm interested in with an exponential effort. So the question is whether we can have rigorous results with a polynomial effort. Or maybe the fact that we have to abandon this idea of going through an exact result because the number of parameters grows exponentially forces us to abandon to have any kind of rigorous certification of the number of parameters. Okay, so this is what motivates us. Yeah, maybe so again, I will repeat the same I was just saying with this table. So you have the exact result. It's not scalable. You cannot reach very large system sizes, but because it's 35, it's actually exact, no? And the variational method, you can reach very large system sizes, but you have no rigorous certification on your property of interest. So what we showed recently, and some other people as well, is that if you use the polynomial optimization techniques that you may be familiar with, then somehow you can get, and this was with Victor, who is not here, but he was yesterday. He knows what I'm going to talk about. So what we proved is that if you take these polynomial optimization methods, in a way you can get the best of the two worlds. Okay? So you can have certified results in a scalable way. And this is what we want to understand. We want to understand the possibilities that these techniques offer for the study of many body systems. So just to understand, this is the picture I was showing, which you have this exact result or the variational result. What we are doing is we arrive to bounds, rigorous bounds on the quantity of interest with a polynomial effort. We don't get the quantity, we only get bounds. Sometimes the difference between these two bounds is very small, so effectively we get this number. But the important thing is we do it that with a polynomial effort. So if you hear what I'm saying, I think okay. Good. And
at least with the assumption that ground state is fixed now,
this is the definition of the ground.
So you said that you were assuming that you were not simplifying.
Okay, so what I say is that in principle, in principle, we have to compute the minimum over all states. Okay, then what we will do is they restrict to a minimum. So I'm not going to restrict anything. Okay, so this will be valid. These are valid for this number that is computed over all states. So this is why it's rigorous, okay? Because I'm not restricting. Yes. Yeah. More questions? Good. I think it's my fault. Okay. So now this is something that you know, but this is the concept that we're going to do. So again, we are facing a complex problem because there are many parameters involved. So the strategy I'm going to do, I don't say this in front of my students, but we are going to relax, okay? And the way we are going to relax to face this complex optimization problem is through something called hierarchy of semi-definite programs for polynomial optimization. That does not sound a very relaxing term, but this is what we're going to do, okay? And okay, here maybe you may know many of the terms here, but when I do the talk, I'm going to tell you a bit explain you all the ingredients that you find in this terms. Okay, this is what you have to understand. So you have to understand our motivations. Now you have to understand the methods we use. Who knows about these things here? Okay, many people. So this, okay, it will be a bit boring for you. For the others, I hope you will follow what I'm going to say. Okay. So how to explain these terms? So the first term, the exponential optimization. Well, I think this. I'm not sure if I need to explain it in this audience, okay? But this polynomial optimization, so you want to find the minimum of a polynomial subject to some polynomial constraints. Okay, so what is an example of polynomial optimization? This polynomial standard polynomial optimization over what I'm going to say standard variables, classical. Okay, it's an instance of polynomial optimization. Well, these problems in functionality are NP hard, so these are difficult. What I do? Okay. Yes. So this is the problem I want to solve. So what I'm going to do now, I'm going to represent what is happening now. So this is the polynomial I'm going to represent with this line, and I'm going to do a brutal simplification just for the sake of illustration. So the region, the feasibility region, the region of points that satisfy these constraints, I'm going to represent by this gamma hat. Okay, it's not complex in general. It's simply because I was lazy when drawing the picture. And now, what is the solution for that? Well, problems with this. Okay, I guess we all know that this is the solution, right? I mean, this is a minimum, but it's not in the feasibility region because it is a problem in veracity. Okay, good. So, an approach to solve these problems was introduced by Lasserre in Toulouse, and what he did was. Okay, what he did was, okay, I'm not going to solve this problem that is hard. I'm going to solve this problem over another set, okay? And actually a hierarchy of sets that I'm going to call gamma k. And he designed these sets. So I replaced the problem, the feasibility region by some other regions of space in the space of parameters. And it happens when you make this replacement, the previous problem that was NP hard becomes an instance of semi-definite programming, which is a technique in convex optimization theory that you can solve efficiently on your computers. So he took a complex problem, replaced the region in which you explore the minimum by another region, and then you can solve it. Although you're not solving the original problem, you're solving a different problem. Okay. Now, if you want to understand what's happening, this gamma k that I defined here, you can prove that they are outer sets that contain the region of interest. And these outer sets get tighter and tighter when you go higher into this hierarchy. So the hierarchy is these outer approximations that converge to the set of interest, and you solve this problem. So what happens when you solve a minimization problem of a larger set, you get a lower bound to the solution, okay? And you have a sequence of lower bounds that, since these outer approximations converge to the feasibility region, they converge to the actual minimum. Is it clear what I'm saying? Okay, this also answers your question, so I'm not restricting. I'm actually enlarging the set of possibilities. Okay, but the good thing is that I have the promise that this is included. This is convex optimization. There are no problem of local minima or anything like this. So I get the actual minimum. So this is why the results are certified, and this is why it's a sequence of lower bounds. Good. So this, for instance, you can use it if you are interested about classical spin problems. This is an optimization over spin variables. Okay, spin variables, usually these are numbers that take plus and minus 1. So you want to find the minimum of this over this constraint. You are imposing that the number is equal to plus and minus 1. And everything is polynomial. So you will get, if you apply this hierarchy to a classical spin problem, you get a sequence of lower bounds to the ground state energy. Okay, this is interesting. I mean, people are aware of this. Because what people, for instance, if you have a classical spin problem or an optimization problem, people sometimes use Monte Carlo. Monte Carlo is an instance of variational methods. So Monte Carlo for those who know, you are exploring some a landscape of possibilities. You want to find again the optimum of your quantity, which is this. And Monte Carlo somehow finds this and at some point stops. And you never know whether you have got the actual solution, the actual minimum, or you are far from that. Okay. Okay, this is the value intensity. So having a lower bound is good because at least you have some control about it. This was not. It's not. Okay, so what is the method we are going to use? We introduced this method in something called Bell inequalities in quantum information theory, but then we realized that what we were doing was taking the non-commutative analog of what Lasserre did for the classical case. So I'm going to take polynomial optimization, but now I'm going to do it over operators or non-commuting variables. Okay, for quantum physicists, this is what we care about in general. So now we have a polynomial over a set of operators, and I want to find the minimum of the excitation value over states. Okay, I'm just somehow taking the previous formulation and replacing numbers by operators. So remember there was a polynomial here, and then the constraints, it can be a bit more, it can be more general than this, but it's just a polynomial over some operators that are now operator positive. Okay, this is non-commutative polynomial optimization. But what we did was basically the same. So there is a number here that we want to obtain, and we found other approximations to the set feasibility region, and each problem is a semi-definite problem, so we can easily solve it. So we get a sequence of lower bounds to the solution we're interested in. Okay, I don't have time to tell you the details. You can go to the papers, but basically what we were doing, actually we found the method, and later we understood that we were doing non-commutative polynomial optimization. Okay, so this is useful now if you care about many. But again, we did that. I mean, I also want to remember something from my talk. So there are several take-home messages. So one of them is that if you care about quantum problems, there are many instances of optimization over operators. Whenever you are facing one of these instances, think about my talk, my papers, and cite them. Okay, because we have a possibility for you to solve these problems. Okay, so possible, again, we introduced this in the context of Bell inequalities. I'm not going to talk about Bell inequalities. I'm going to talk about Hamiltonian operators over spins. So this is a polynomial. Okay, so you take this polynomial made of Pauli's spin 1/2 particles, sigma x, sigma y, sigma theta. Okay, so everyone knows here about what I'm talking about. Okay, and then you can apply the machinery I was telling you, and you will get lower bounds to the ground state energy. Now, I want you to understand, I'm going to change a bit the language for you to understand what it means, this concept of outer approximations. Sometimes are also called relaxations. Okay, you relax a set of interest, and you take a relaxed set, an outer approximation. I want you to understand in this context. So this is the problem we have to solve. Now what I'm going to do, I'm going to take the state inside. Okay, usually Hamiltonian is a combination of, say, products of Pauli's. Okay, it's the polynomial on the Pauli's. Okay, you want to understand what I'm saying? So what I do now, I take the state, I put it here in the dual and the other one. I compute the scalar product. Okay, so I put it inside. Now, if you look at this, it looks like a rather easy problem. Okay, I only have a linear combination of some numbers. Okay, scalar products. These are numbers. Okay. And these are numbers over operators that act on two sides. So these are just matrices of size, small size. Okay, so what I'm doing now, I'm taking product of Pauli's. Pauli's act on one particle, say one qubit, one C1 particle. So this looks like a very innocent combination. Why is it so difficult? Well, the problem is difficult because characterizing those numbers, those scalar products that come from an n particle state is very difficult. Okay, this is sometimes called this is a very famous problem in quantum physics. It's called the marginal problem. So I want to identify over a state of many particles the reduced states, the state of subset of particles that are available. This is why, otherwise, the problem, you are considering a Hamiltonian made of very few qubits, or very few terms acting on very small subset of qubits. This problem could be easy if characterizing this set of numbers was easy. Okay, so this problem is difficult with characterizing these expectation values of some operators over a big quantum set is difficult. Okay, so I'm just rewriting what I just said. I'm just rewriting this into this minimization of this quantity in this new language. I'm going to call these are the expectation values or moments, the quantum moments. Okay. And what our method does is you replace this set of quantum moments by another set of numbers that includes those numbers that have a quantum realization. We understand the method saying, okay, what we do, we take some, at the very end, a polynomial is made of excitation values, scalar products. The difficulty comes that it's very hard to characterize those scalar products that have a quantum realization. And our method does, it does sets, outer sets that have the set of quantum moments inside. Okay, so this is what I was saying. Okay, so basically, this is the problem we need to solve. You see, here now this problem is linear over this set of moments. We have these conditions here, and the method what it does, it approximates this set from the outside. Is it clear on what I'm saying? Okay, so just to summarize what is happening here. Again, this is the set of quantum moments. Now the quantity we are interested in is a hyperplane. You follow what I just said. The number you want to find is this one. Okay, this is the tangent hyperplane to the set of quantum moments. In variational methods, you explore a subset of these quantities, this tensor network space that Frank was talking about. This yellow region. A problem you have with this is that these subsets usually are not convex. So you don't have guarantee that you are in the minimum. And what we do, we have an outer set, so we get a lower bound. So you get an upper bound from the variational method to the ground state energy, and with our method, you get a lower bound. The difference, and this is important for what I'm going to say, the outer approximation is convex. So you know that you have the actual minimum or maximum or whatever. Okay, but this was somehow less known. In this paper, we did all my explanation so far. I'm focusing a lot about the energy. Okay, so I have a polynomial which is the Hamiltonian, and the expectation value is the energy, and I'm talking all the time about this, about energy. So in this paper, we realized that you can go beyond energy. And remember that at the beginning, I was telling you not the energy. I'm interested on magnetization, another property. Okay, and now I'm talking a lot about energy. So what we realized in this paper is that using this polynomial optimization, you can get bounds not only on the energy, but on any property of the ground state, in particular magnetization. Okay, so this was, I'll say, the main insight we had in this paper, that you can use this polynomial optimization to get bounds not only on energy, but on any quantity of interest on the state of the energy. Okay, so this is what I was telling you. If you want to find the magnetization exact, you get it, not scalable. Variational, you get a state, hopefully close to the ground state, and you get a value, hopefully close to the ground state. Or you can use this relaxation trick with this polynomial optimization. Then you will get a lower bound to the energy. Actually, these relaxations also give you something that you may interpret as a value for your observable of interest, say magnetization. But you have no clue, again, how close this is to the value you're interested in, whether it's a lower, upper bound. Okay, so this was, I would say, the state of the art before our paper. So what we did is that if you put the two things together, you can certify any quantity of interest, and this is what I'm going to tell you about. Okay, so you can get bounds on energy, magnetization, basically on any polynomial acting on the ground state. In fact, the only thing we need.
So you don't need any one of these with respect to the other, for instance.
I only need actually an upper bound on the ground state energy. Actually, then there were some other papers in which people realized they didn't even need that. But in our case, this is what we use. Okay. I mean, there have been some improvements, and I think, okay, I'm going to tell you about this, and then you can also look at the other, because this is what. Okay, so let me just go back to what I was telling you. Remember, this was the Hamiltonian, if you remember, defined by this polynomial of Pauli's. Okay. So this was what I tell you about the energy, that we replace this, we relax, instead of doing over quantum scalar products, we did it over a set of scalar products that included the quantum one, and this is why we could get a lower bound. Now you may say, okay, tell me the operator you are interested in, say magnetization. Any operator is a polynomial of Pauli's. Okay, Pauli's is an operator basis for any operator. You can always write any operator as a combination of Pauli's. So I can take any operator, I write it as a combination of Pauli's, and then I repeat the same. I minimize over states the value of this operator. So take magnetization, okay? Remember, it's sigma z in particle 1 plus sigma z in particle 2 plus sigma z in particle 3 plus sigma z in particle n divided by n. Okay, it's a Pauli. So I can play the same trick, but now instead of doing for energy, I do it for magnetization. Okay, if you do that here, okay, what is the minimum value of magnetization? Okay, it's sigma z everywhere divided by n, so the minimum value is -1, and the maximum is +1. Okay. So if you do this here, you will get -1. Okay, because you're optimizing the value of magnetization over all possible quantum moments, all possible quantum states. So you're going to get -1. Not very, I mean, getting bounds on quantities, I can give you a bound of magnetization, -1 and +1, but it's not very informative. So then what you have to do is like, wait, if you give me upper bound on the state, on the ground state energy that, for instance, I can get through these variational methods, this is again a polynomial constraint. So I put it there. So I'm not looking at the minimum of magnetization everywhere. I'm looking at the value of the minimum of magnetization over all states that have an energy smaller than the upper bound. So now you saw this with our method is again a STP, and you will get a non-trivial bound on magnetization at the ground state. So actually, it's a bound on magnetization for all those states that have an energy smaller than EA. So if your upper bound is good and close to the ground state, okay, there are not many states with this energy, and you will get a non-trivial bound on the quantity. And I can do that because everything here is polynomial optimization. This is what I was telling you. Whenever you have something on polynomial operators, go to my papers. It's a joke. I don't know anymore people doing these things, but just remember that there are techniques to deal with this polynomial optimization. And this is an instance, okay? So just for you to understand, this is what we do now. So we take the operator of interest, we express the Pauli, and then this is a problem we have to solve. If you do a minimization, you will get a lower bound on the minimum, okay? And you get the lower bound, your quantity of interest, and if you take the maximum, you will get an upper bound, and then you have the rigorous bounds on the quantity of interest in the ground state. Now, how does it work in practice? Okay, then, okay, in something that you realize in many body physics, what I'm new in this, so for me, it looks like a many model theory. Okay, there are zillions of Hamiltonians in which to deal, in which to you can benchmark. We chose something that is known, and it was also good for us because it has a lot of symmetries, which was a Heisenberg model. So this is first we took a chain, and there is interactions between neighboring particles. Okay, you see I and I plus 1, and the interactions are xx, yy, z. Okay, so here in this one. Okay, so this is a model of 1D chain. Okay, you can forget here about the orange light. So first we tested the energy, and this was, you don't see it, but then you see here a small difference. So this is the upper bound you get with variational method, and this is the lower bound on the ground state energy you get with our method. So basically here we are certifying the ground state energy up to a very small difference. Okay, the ground state energy there. And this we could do up to 100. Now we have improved these numbers. So we have a recent paper in which, especially the first author, G1, he has a very good code, and he could go up to, for sure, more than 100, maybe 200 or something like this. This is 1D chain. Okay, so here the energy works very well. And we also consider a second model in which we have interactions between neighboring particles, but also next to neighboring particles. Then we have I plus 1, I and I plus 2. And this again, the energy, the upper bound and the lower bound on the energy. This is, we are using something called DMRG, which is a standard variational method for 1D systems. Okay, you see the difference is also quite small. So basically here, I'm certifying to you that the ground state energy is for this curve here. But as I was telling you, the interesting thing is that we can do things beyond energy. So for instance, you can take people sometimes care about how two body correlation functions, so whether spins are aligned or anti-aligned. Okay, and this is the value we got with the MRG. So for 1D systems, the MRG basically everyone believes and gives you the solution. And this is our upper bound, and this is our lower bound on this quantity. Now, is this good or bad? Well, for sure here it's good. Okay, we are solving the problem. Okay, I don't know. For me, knowing that the two-body correlation function is between 0.02 and 0.04, it looks good enough. But I don't know. Maybe Filippo will complain. Yes, you tell me. Okay.
I mean, usually you're interested in phase transition, so I mean, you need to be able to resolve the critical exponent or criticality. So it's not about this.
Sure. Yes.
It's about two different quantities. If you can resolve which is which.
Yes. So yeah, so I think we should understand also that something that we didn't do is to compute critical exponents. No, but okay. For now, in the context of phase transitions, no. Sometimes you want to know whether when changing some parameters, your Hamiltonian spins are, for instance, say a very simple instance of phase transition is that sometimes spins pass from being aligned to being anti-aligned. Okay, this is a change of this parameter or sign. Well, here I can certify that there is a phase transition at this point because here the lower bound is positive and here the upper bound is negative. So here, for me, these bounds are good enough in this instance. I don't care about whether there's a gap or not, because I know that here there's a change in these properties of the spins, which change these parameters. Actually, we have a paper, I don't have time, in which we use this for phase detection.
Say that because the value gets worse on the left top, that this is an indication of phase transition?
No, this is not a phase transition, but let's say sometimes phase transition are associated to the change of sign in another parameter. I haven't studied, we haven't studied phase transition, but if it was, in this case, this was the parameter, okay, this would be a way of certifying the phase transition, which is not possible in variational methods, okay, because if the phase transition was defined by the sign of this parameter, here I would certify, okay, here there is something that changes, okay, because here this value of this correlation function is positive, and here is negative. Okay, so the spins are aligned and aligned. This is, I can certify to it.
Because then at this point also...
Because here the upper bound is negative, so the quantity is negative for sure. And here the lower bound is positive, so the quantity is positive for sure.
But in principle, your method should not care about critical, like for going from critical to non-critical.
Yes, okay, so this is an interesting question. Where the method works well and when it works bad? I don't know. I mean, blindly for me, it's just polynomial optimization with some parameters changing the polynomial. But for some regions, in some cases, the outer approximation works. It's very tight, and some others not.
So for matrix processes, we know that they fail in critical systems.
Yes, but here I don't see why it should.
But I think because you have a phase transition at that point, the big question is if there is an intermediate phase exactly at 0.5, and like that is sort of settled, but it has been a super hard question to answer. And the two phases are very different. But one to the left is super simple as operators is an antiferromagnet. So I think you just need a very simple let's say expectation values of operators to represent it. But to the right is much more complicated.
Yes,
so
look,
it's very
yes, I'm not a many body physicist, so you know much more than me on that. I just tell you how these bounds behave in a system. What do you want to do? Well, thank you. But yes, so I don't know. Okay, so we took this because we thought it was a good model, and we don't have. I think a good question is to understand why, when it works well and when it doesn't, it should be related to the physical property of the system. I mean, formally, it's just a polynomial optimization, and then we went to 2D models. Okay, so here, for instance, you look at the energy, the work was not that good. Okay. Assuming, okay, we may say that we are not good, or we may say that the variational method is not good. Who knows who is right? And we also had cases in which our upper and lower bounds were bad. So here, I'm already saying that they are bad. You see here, this is a 2D system, a square, and these are the correlations between a point in the middle and the upper right corner, and the upper and lower bound is system size diverged with system size. Okay, here we are bad. bad or not good enough. We have also improved these numbers lately. Okay, and then we computed some other. For 2D, we struggle more. But what I want to tell you is that sometimes with 2D we found difficulties to find numbers to benchmark with. Okay, because even variational methods struggle with 2D. And for instance, we had a recent paper in which, with these methods, we can reach system sizes of size 16 times 16. Okay, so sometimes these methods, we are working on that, but they reach system sizes that are not bad, especially in 2D systems. Now, I'm going to tell you another instance of this polynomial optimization. I was talking a lot about ground states. And again, there are many problems in many body physics that people are interested in. Another one is related to what I'm going to explain here. The simplification of steady states. This is something that we realized in this paper. Actually, also Robichon and Tillois also realized of the same. And basically, what we want now, we have a different problem, so not energy. So we have a system that is called in physics open. So this system is interacting with something else, with this environment. And then what happens in this system environment interaction is that if you wait long enough, usually the system, okay, anyway, so it tends to something called the steady state. Okay? So you wait long enough, the system usually arrives to a single state. Well, this is not the case, but you have a steady state, and people care about the properties of this steady state. Okay, again, reconstruction of the steady state is complex because it depends on many parameters. We want to understand whether there is a current in the steady state or again magnetization. So this is something that we. So what happens is usually we look at some dynamics that are described by something that are called Lindbladian operator. So you have the state of your system varies with time, and the variation is given by this Lindbladian operator that has this one. Okay, this is very standard in the study of open system dynamics. So what is the steady state? The steady state doesn't change with time, so it has to be L rho equals 0. Okay, so what is that? A polynomial equation in rho. So then when we saw the polynomial equation, we thought, okay, here we can do something. So we could use these polynomial optimization techniques to do something similar to what I was telling you and bound properties of the steady state because it's defined in sort of polynomial language. I'm not going to tell you about these original papers. I'm going to tell you very quickly about something that Miguel will explain in this afternoon. So he will give all the details, which is we also prove the certification of many body steady states. So I'm going to go very quickly here because he will explain. So basically, we were studying Lindbladians that have a local form. So qubits interact with neighboring particles. And in that case, we can also use some sort of relaxations that are semi-definite programming. He's going to tell us about this. What I want you to see are the results for 2D, okay, because I think are pretty impressive in the thermodynamic limit. So this is an infinite size system. And here we are plotting sigma z for 2D, okay? And you don't see it, but there is an upper and a lower bound in the red part. So basically, we are solving the problem. Okay, here there is an upper or lower bound of this system. Okay, so this is 2D infinite size steady state sigma z for the steady state. I think it is remarkable.
Yes, good question. If the state is very classical, as opening also very mixed, very high rank, is it easier for you or?
So you mean the steady state is not rank 1?
No, it's very high rank.
Yes. Okay, then by definition, we'll get a difference in the bounds, okay? Because magnetization, then we're looking at the steady state degeneracy. And that's maximizing the value of an observable over all states in the steady state subspace.
So this is harder for you.
Well, it's not harder. We'll get a gap between the two bounds. So you can think that this is also a way of detecting or smelling degeneracy, okay? So when you change, we have seen this in some, saw this somewhere. So you see that the bounds are very good, and then you arrive to a point in which this happens, and they are large. Okay. I think it's maybe somewhere in my, he will for sure tell about these things. Okay, so I'm excited. I don't know if I'm conveying this to you because I think it's a new paradigm. So for many body physics, because of what I was telling you. Okay, so it has, you can get certified results for many body systems in a scalable way. So when I say scalable, I mean that if you fix the level of the outer approximation, the effort grows polynomially with system size. Okay, this is why I'm saying scalable. In the same way as variational methods are scalable in the sense that if you fix the bond dimension, the system grows polynomially with bond dimension with system size. Okay, we are not the only ones exploring these things, and there are also papers by Foti Scarlett and also by the people here, Miguel Navasquez. We also had a paper that again talk about on how to use these methods for phase detection. Okay, I will be honest. We are far, far from being as scalable as tensor networks. Okay, in principle we are, but you see, I don't know if you can see, this is not dark green. Okay, so we have to work on that. I also want you to understand that I think the comparison is not is system size or what you care. So variational methods, they tell you, okay, solve this problem for say 1,000 particles. I estimate that the quantity you are interested in is 0.3. And what we say is like, okay, for a system of 300, not 1,000 or 100, I can tell you that your quantity of interest is between these two values. So they give you different information. So I don't think that we should be obsessed by system size being the only parameter. I think this is a valid alternative complementary to the others, and we should explore. I want people to explore the potential and limitation of this alternative. Of course, if we can reach the same system sizes as a rational with a small gap, then we did, okay, because we did rigorous results. But I doubt that this will happen. Well, I don't know. We should work on these things, and what is one of my obsessions. And I think this opens a new paradigm, no? So because you have the way of answer the main question that we were clear on. Okay? So you have now a way of getting rigorous and scalable predictions for network systems. Okay, so thank you very much for your attention.
This don't have an answer. Do we have any questions?
Thank you very much for your interesting talk. What is the main obstacle for actually reaching the same sort of performance as variation limits?
Yes, so the main obstacle we have is that these outer approximations, it happens often that go. This outer approximation, the first level in the hierarchy. Okay, then I start again. Okay, so it's a hierarchy of sets that approximate. So you may say, okay, why do you need a hierarchy? Just start with the lambda k with the k as large as possible. This is because the matrices involved in the semi-definite program, the size of the matrices grows with the hierarchy. So solving the SAP for gamma 2 is harder than solving for gamma 1. Okay, but have to be, okay, because this tends to when you're solving a very difficult problem. So this is why usually what we do also is like you start with gamma 1, you see the bounds are good, and then you stop, if not, you go higher. Heuristically, in the case of inequalities where we do the hierarchy, the first level works reasonably well, but for many body substance, we see that the first level does not work that well. So we go higher. If you fix the level in the hierarchy, everything is polynomial, but the polynomial is sometimes n to the k, where k is the level, okay? Then, yes.
So you are exponential in the order.
So things go very quickly here in the hierarchy, but for a given level of the hierarchy, and polynomial systems. Yes, but it's a polynomial, but not so good. So this was, I think, for us, something very important is to collaborate with the group of Victor Mandron. So they had a code in which you exploit symmetries and sparsity, and this is where, for instance, we could create a system of 16 times 16. Okay. Having said that, also something that I find very interesting is that these methods, there are variants of these methods in which you can deal with a thermodynamic limit, so infinite particles, and you get a response on the thermodynamic limit.
Any other question?
Okay. So, it part already answered, but do you have an understanding of, let's say, at those orders, what constraints are useful and what are not? So symmetries give you something, but there is, for example, when we use variation methods, we know that the correlations decay exponentially, which is not as rigorous as a hard constraint, but it helps us. Can you think of a way to throw this sort of information in it?
Yes. So let's say two things on in this direction. Okay. I think this is something that we would like to do because okay. So our formulation of polynomial optimization was you minimize the C over the state and the operators. That was the formulation we introduced in the context of the inequalities. Now, if you go to a Hamiltonian problem, you don't optimize over the operators. They are given by Paulus. It's an easier instance, for sure covered by this, but it's an easier instance, okay? So you have more information about the physics of the system. So that's something we did for 1D and 2D, you say it's local. So we don't put terms of particle 1 talking to particle 100. So we remove that from our approximation, okay, from our moments. Okay, I don't have time to tell you about this, but we use this information. I would say this is quite basic. One of the things that we need to understand to reach larger system sizes is how to use this physics intuition. I would say one of the problems we have is that this is a very general formulation of the problem. So now we have to, sometimes when you have a general formulation of a problem and you want to deal with a specific problem, it doesn't work so well. So you have to understand how to massage it into, and this is what we have to do. Like, yeah, understanding the property of it that you suspect from system interest. So this is why also I think the information you get from variational methods, you should understand how to use it in the polynomial optimization. It's a very vague statement, what I'm doing. But
with variational methods, we get the point, right? And sometimes we don't care about having a rigorous bound, but we would just like to know, okay, if I move around here in the Hilbert space, not in the variational manifold, but in the Hilbert space, which is where we cannot go, like, do things change drastically or not? Because, let's say,
well, but if you can put this into the bounds, no? You see that the bounds don't change much, then this is, like, I think it's something to consider. Like, this is what Miguel was seeing in the steady state, I was telling you, So he saw that the bounds, correct me if I say something wrong here, okay? So he saw that the bounds, the gap was small between the upper and lower bound, and at some point it was growing. But it's just telling us that probably there is degeneracy in the steady state at that point.
Any other question? And I actually have some, but I would like to. You asked about excitations because in the variational community, excitations came also after ground state search. So is there like already?
Not that I'm aware how to put the excited states. We tried a bit. So I think also an interesting problem, maybe for people with a more formal background, is how to accommodate relevant physics questions into this language. Okay, so that's something that we are doing with my student who is not here. He was interested in putting partition functions and free energy. So you have an entropy. And for instance, Miguel Navas and co-author, they have a paper in which they put the exponent that you have for dynamical evolution into this language. Okay, and then they can get upper and lower bounds of the value of observable under dynamic evolution. Well, not surprisingly, the bounds get worse and worse with time. Okay, but I think an interesting perspective is I focus a lot on polynomial optimization. I think this is a possibility, but even the concept of convex relaxation is interesting, and I think it's interesting formally to understand which physics problem, entropies or exponents can be put into this language. Because since the convex relaxation, again, you keep convexity, then problems become sometimes you relax, easy to compute, but since it's convex, results are rigorous.
Okay, now
And for the Navasquez paper, do you think that there could be like a bonds at and convergence rates, or like the paper as they had it inserted by an archive?
The one that on exponents.
Yeah, the one on the time evolution.
Yes. Okay, I don't remember now, but
It's very high level, like
Yes.
compared to your like SciOp paper This is more like the.
I only,
physics.
to be honest, I like Miguel, but I didn't read his paper. I know what he does, but I cannot tell him. So. No, yes. But if you think about entanglement, no? Well, there are some results, but I would say it's open how to do it for entanglement. Because if you care about appeals, you will say, I want to compute the entanglement for the ground state. Okay. Well, it's difficult because do you know about entanglement? Okay, so usually a measure of entanglement is the entropy of a subset of the particle. Okay, the entropy is not a polynomial. That's why I'm saying we need. Okay, you could put maybe purity of the subset. Yes, but purity is a polynomial over state. And if you remember my formulation, it was a polynomial over operators with state only appear linearly in my formulation. Okay, so there are also variants to put polynomial over even states. Okay, but I think all these things formally are interesting. At least I find them interesting, or to accommodate things in this language. Also, I think I like it also if you think about the many body again. We should think about ways of forgetting about states. Okay? States. I think I like it. Frank yesterday was showing a paper in which he was showing Hilbert states as a fiction or states as a fiction. Okay, when you go to the many body state, it's regime. It's an illusion of the state. I mean, it's just a exponentially never accessible list of numbers. So we should think about other ways of getting predictions without going through the state. And all these techniques I'm telling you is a way of getting this potential polynomial.
Because for the gap local level versions, the ground states are going to have bigger law and they're very lowly entangled.
But this is connects with so you suspect that the system is gap and then correlation will be exponentially. We are using this thing. So in our methods, we don't put terms that involve a spin and a very far spin because we know that this is because they allow the correlation will be small. So this leads a bit in the relaxation. Sometimes we shape the relaxation to the property of the system. So we should use this.
Okay, if there's no other question, then we thank the speaker.
Thank you. I put it on. Yes. Thanks.